Hello everyone, I'm Varun, Assistant Professor, Department of Mathematics, SJB Institute of Technology.
Hello everyone. Today we are discussing method of variation of parameter. As you know, in module 2 differential equations, we have already solved homogeneous differential equations, and while solving non-homogeneous linear differential equations, what we saw is we saw three kind of particular integrals. Okay, in type 1 we saw e to the power of ax, the exponential function. In type 2 we saw trigonometric function, either sin ax or cos ax. In type 3 we saw polynomial, okay, algebraic function. For example, if I have any polynomial, how to solve using division method. Now, keeping all these aside, is there any chances of having a linear differential equation? Okay, and other than sin x, cos x and exponential, or combination of these. So keeping these things in mind, we will just see about the new method known as method of variation of parameter. For method of variation of parameter, consider a linear differential equation of second order given by the form d square y by dx square plus p dy by dx plus qy is equal to r, where of course p, q, r are the functions of independent variable x. Whenever I say x, it is denoting independent variable. Okay. If the complementary function of this equation is known, then we can find particular integral by using method of variation of parameter. In the next stage, we will look into the working procedure of finding particular integral using method of variation of parameter. Okay, just like the first three types of finding solution to the non-homogeneous differential equation, we will first find the complementary function of the given equation. Okay, but we will write it in the form of y is equal to c1u plus c2v. Okay, as you know, c1 and c2 stands represents constants here, and u and v are the functions of x. When I say x, it is independent variable x. Okay, in step 2, what we will do is we will assume, okay, the solution of the given differential equation to be of the form y is equal to au plus bv. Of course, here c1 and c2 in the first step is now replaced by a and b, and a and b are again functions of x, which represents independent variable. So our assumption is y is equal to au plus bv, which where a and b are functions of x, is the general solution of the given equation. In step 3, we will find w. W is equal to uv dash minus vu dash, or the better representation of the same formulation is w is equal to, it is represented by a determinant. In the first row you will have u and v, and in second row we will have its derivatives u dash and v dash respectively. Of course, working out we will be getting the same formula, uv dash minus v u dash. Okay, and in the fourth step we will assume the expressions for a dash and b dash. As you know, in the second step we just replace c1 c2 by a and b, where a and b are functions of x. Okay, now in fourth step we are assuming expressions of a dash and b dash. A dash means da by dx, b dash means db by dx, is of the form da by dx is equal to minus vr by w. Okay, the w which we found in step 3. Okay, and db by dx is found by using ur by w, the same w which we found in the previous step, right? Now our main target is finding a and b, the functions of x which we assumed in step 2. Okay, keeping that in mind, we already know two expressions is assumed for a dash and b dash. So concentrating on that, in step 5 we integrate a and b containing of course a and b each containing a constant, and hence the general solution is given by y is equal to au plus bv. So the main intention of step 5 is to integrate the previous expression da by dx and db by dx, and find the values of a and b, which are in fact the functions of independent variable x. Okay, and I would like to mention one more thing here. W, the step 3 we mentioned about w. W is very famously known as Wronskian of functions u and v. Okay, if you people are asked to find Wronskian of two functions, the procedure is to find W is equal to UV dash minus VU dash. Okay. Now in the next stage, we will solve a problem, okay, using method of variation of parameter. In the first case, I am considering d square y by dx square plus 4y is equal to tan 2x. Okay. So previously we have not seen tan 2x appearing in any of the problem. In any of the non-homogeneous problem. Okay. So the first step, as I told you, is about finding complementary function. So initially we will write the given equation in symbolic form. In symbolic form, as you know, it reduces to d square plus 4 into y is equal to tan 2x. And of course, when I say d square, d represents d by dx, right? So thus the auxiliary equation is given by m square plus 4. Of course, replacing d by m, we are getting m square plus 4 is equal to 0. So it obviously implies m is equal to plus or minus 2y, which is a complex case. Roots are complex. So complementary function will be given by c1 cos 2x plus c2 sin 2x. Now in second step, we will assume y is equal to au plus bv is the general solution of the given equation where a and b are functions of x. So it obviously implies me u is equal to cos 2x and v is equal to sin 2x. Also comparing with the standard form, I am getting p is equal to 0, q is equal to 4 and r is equal to tan 2x. Now using u and v value, I will calculate what is w, the Wronskian. So u is cos 2x, v is sin 2x. Different derivative of that is minus 2 sin 2x and the derivative of sin 2x is 2 cos 2x. Finding determinant, I am getting w is equal to 2. Okay, now for better understanding, we will calculate what is VR and UR. The value of V is sin 2x into R tan 2x. I am getting sin square 2x by cos 2x. And on the other side, UR is cos 2x into tan 2x, which is giving me sin 2x. Now, A is given by minus of integration of VR by W. Of course, VR by W is already, we will substitute that. We will get sin square 2x by 2 cos 2x. Sin square 2x is split as 1 minus cos square 2x. And of course, splitting the term wise, I am getting 1 minus cos 2x as secant 2x minus cos 2x. Integration of that is log of secant 2x plus tan 2x minus sin 2x plus c1. Integration constant should never be forgotten. In the next case, b is integration of ur by w dx plus c2. Okay. So in this case, what I will be doing is I will be substituting ur value to be sin 2x divided by w value is 2. Of course, integration of sin 2x is minus cos 2x by 2. And of course, after working out, I am getting b value to be minus cos 2x by 4 plus c2. And the general solution, as you are aware that AU plus BV is the general solution, I will substitute the value of A and B. Now we will simplify it. After simplification, I will leave simplification as an exercise. After simplification, the general solution will be of the form C1 cos 2x plus C2 sin 2x minus 1 by 4 cos 2x plus log of secant 2x plus tan 2x.